growing a better world together. Quite the goal we set there. For such an ambition, we need the right skills. And as developers, we code. So let's sharpen those skills and start coding a better world together. This first edition of Coding a Better World Together is on clean coding and clean architecture. And who better to teach us more about this than Mr. Clean Code, aka Uncle Bob, the one and only Robert C. Martin. And here are your hosts for today. Hans Kluppers and Theodoros Weiss.
Hello, everyone. I said, hello, everyone. Welcome here today at Rabobank for the second day of the Clean Code and Clean Architecture event. I'm Hans Kluppers. And this is Theodoros. We will be your host for today. When you want to share something about the contents of the talks of today, you can do that via Twitter. You can use the handles you see above. When you have something to say about the organization, the facilities, or behavior of people, you can address that with me or one of the people in the blue shirts. We are here to help you and want to make it a fun event for you. Theodoros, would you like to say something on behalf of the Utrecht Jeugd?
Yeah, thanks a lot, Hans. Welcome, everybody. Good morning. I hope you will enjoy our great program for today. On behalf of Utrecht Jeugd, I would like to also share that we are really honored to be co-hosting this great event today. I will not be saying yet why this event will be great again today. We've been organizing quite a few events for the past 3 years. However, today is a big day. Also, something more, a warm welcome to the people who are watching us from the live stream. And Hans.
I think we invite Dick Vlot on the stage. Dick is our chief architect of Rabobank. And he wants to give you a welcome on behalf of Rabobank.
Good morning, everyone. Welcome to the second day of this event with Uncle Bob. My name is Dick Vlot. I'm the Chief Architect of Rabobank. And it's a pleasure to welcome you all here in the Rabo Auditorium, which we use for internal gatherings, but also for external events like this one. So also a warm welcome to all non-Rabobank IT colleagues here in the room and the people who are joining us on the live stream. I hope you are able to stay with us for the rest of the day. It's a real pleasure. I'm actually excited to have Robert or Bob Martin here today. He brings a wealth of experience and insights in IT, so much that many of us like to refer to him as Uncle Bob, and maybe he'll explain to you later today how that Uncle Bob name came to him already a while ago. I'm pretty sure that every one of you works at the moment in an organization where the Agile way of working has been adopted big time. So do we here at Rabobank. We have around 400 DevOps teams working Agile. Because we are, that's quite a group, we are also applying scaled Agile techniques to keep that all a little bit together. And as we speak, we are taking the next step in transforming ourselves to work biz DevOps. So we're applying the Spotify model with tribes and squads and chapters, And because there are so many of these IT squads, we also have an intermediate layer called areas between the tribes and the squads, and that's where we're moving to. The aim of that is to create biz DevOps teams with as much autonomy as possible, so that helps us to get speed and agility in the organization in our digital transformation. Now, some Agile evangelists will preach that with emergent design techniques you don't need architecture anymore, and architecture is a dying métier. As a chief architect, of course, I have a little nuanced view to that. I think emergent design is something that will definitely work in startups and small-scale organizations. But as soon as you start to have some larger scale developments, especially in an organization like this, you need something to glue that together. You need something what Scaled Agile calls intentional architecture, what I would rather call a target architecture, as we always used to call it, but maybe just enough target architecture. I'm not a believer in big design up front. I've seen too many cases where we had hundreds of pages of design up front, and we never realized that. Or if we realized it, we only used a small percentage of that. So no big design up front, but the art is in finding the sweet spot of just enough architecture, not too much, not too little, and also just-in-time architecture, not too late and not too early. I'm sure today we'll further talk about this afternoon. There's also a session about Agile and architecture. We're also using architecture guidelines to help us realize the 3 main IT roadmaps that we have set for ourselves the next 2 years, and I'll quickly walk you through them. The first is our legacy decommissioning roadmap. As a large and already long existing organization, we also have quite some legacy within the bank, but we are pretty far already getting rid of that. So most of the new systems, the more modern systems that we want to use in the future are already here and are already running. And as we speak, we're moving functionality from the old to the new systems. And in a couple of years, we'll be able to get rid of the old systems and we'll be on modern platforms. The second IT roadmap that we are working towards is to the public cloud. Last year, we decided that public cloud is the future, also for banks, and we are moving to the public cloud. The IT for commodity functions, preferably to software as a service solutions, and the rest of our IT preferably to platform as a service solutions to make use of the innovative functions that are available in the cloud, so to make us more innovative. That's the second IT roadmap. And the third IT roadmap is our enterprise data roadmap, where we are establishing a data foundation in the form of an enterprise data lake, which will be the foundation for advanced data analytics, artificial intelligence, and to truly become a data-driven bank. So these 3 roadmaps we are working towards. And within the boundaries of these IT roadmaps, we try to get DevOps teams that are as autonomous as possible. And one way to achieve autonomy for the biz DevOps teams is to try to stimulate them and maybe even teach them to think like architects. And that's what I particularly like about the event like this, where we have a room full of people, not all architects. Most of you are probably software engineers. And if all of you and also business people start to think a little bit more like architects, then we can achieve maximum autonomy of the biz DevOps teams, but still make sure that we have sustainable IT going forward in the future. And wouldn't it be nice if that is what the future will look like? So I'm really looking forward to today. I'm sure you all do. I will be here all day, like hopefully you. Thanks for joining us. I wish you a very inspiring day and enjoy the presentations. Thank you.
Thank you, Dick. Now next we will get to the person we all came for today. But let me first introduce him. Uncle Bob has an impressive career in the IT industry. He has been working there for over 40 years. He had always had a keen eye for what's architecture, what's a good architecture, and how to arrive at it. He shares his view as often as possible, And to give the shortest possible summary of his view, it's about people, not technology. As one of the authors of the Agile Manifesto and the Manifesto for Craftsmanship, he helped the industry to become more agile. But he hates it that the Agile movement is taken hostage by conference organizers and consultants who are so busy with certifying people, Scrum Masters and project managers, that they abandoned the programmers. And with that, they abandoned the values and disciplines of the Agile itself. And I think that's a sad message, but Uncle Bob stays positive, and he keeps on sending the message about craftsmanship. So let me welcome Robert C. Martin, better known as Uncle Bob.
Okay. These lights up here are probably incandescent lights. Probably. I don't think they're light-emitting diodes. They could be nowadays because we can get light-emitting diodes that are very bright, but my guess is that they're incandescent. I think I could figure that out, too. You do carry diffraction gratings with you, don't you? There's some diffraction. Because you never know when you want to know if a light is incandescent or an LED. I carry quite a few of them with me, so I tend to lose them. Yeah, those are incandescent lights, no doubt about it. If there's a smooth spectrum coming out of them, they're incandescent. Now, these things here, I hope they're LEDs. They probably are because they're not hot. Those would be very hot. These would not. Let's see. Oh, yeah, no, definitely LEDs. Well, probably LEDs. Yeah, LEDs, green and red. Yeah, no doubt about it. Those are LEDs. How about these? Yep, LEDs. Why do incandescent lights glow? Why do they light up? Because they're hot. Okay. Why do hot things glow? You're glowing right now in infrared radiation because you're at a temperature of 98.6 degrees Fahrenheit. Why are you glowing? Why do hot things glow? When you hold a piece of metal in a fire, why does it turn red and glow? What makes hot things glow? Energy, good answer, yes. Lacking a bit of detail, though. Why do hot things glow? What is the mechanism? So now imagine that you are an atom of tungsten. That's probably what's glowing up there. The filament in those lights is probably made of tungsten metal. They make them out of tungsten because tungsten has a very high melting point. So you're an atom of tungsten, and you're getting hotter and hotter because there's an electric current flowing through you, and the electrons that are speeding by you are bumping into you and making you shake, and that's what heat really is just the shaking of the atoms. You're a tungsten atom that is shaking. You are composed of charged particles, electrons and protons. So the electrons and protons are shaking as well. Now imagine that you've got one electron shaking. That electron is surrounded by an electric field. Let's say you've got an electron over here that's shaking and another electron over here that is not. This shaking electron is trying to repel this one over here. So as this one shakes, this one begins to shake. How long does it take for those waves of charge to get from this electron to this electron? The waves of charge, this one sets up waves of charge, They move at the speed of light. In fact, that's what light is. Light is waves of charge. The reason that hot things glow is because charged particles are shaking, and that shakes the electromagnetic field and causes waves in the electromagnetic field, which is light. And our eyes interpret that as light. That is why hot things glow. So the next time your children ask you, why do the lights go on when you throw the switch, you will be able to answer that question. Today is all about architecture. And that's a good thing, because every programmer in this room is an architect. To one degree or another, you must understand the principles of architecture if you're going to do a reasonable job at writing code. Because architecture is not one of those things that is entirely high level. Architecture seeps down into the individual lines of code that you write. Now, there are lots of principles about the individual lines of code we write, and we can talk about those another time. But there are also principles at a high level about how software systems are structured. And if the lines of code aren't written properly, you cannot build those high-level structures. The chief architect mentioned something, and it struck me. He said, there are folks in the Agile community who say that architecture is obsolete, that all you have to do is let the architecture emerge. This has always been ridiculous. None of the people at the Agile Manifesto meeting in Utah thought that. We all thought that it was a good idea not to invest massive amounts of time up front trying to design every last little bit of the software, but none of us thought that architectures emerge from nothing. And if you had polled any of us back then, you would have heard us tell you that no software system can be assembled at any kind of scale unless some thought had been put into what the structure of that software system is going to be. So let me dispel that particular illusion right now. Agile is not the absence of architecture. Agile is simply a framework in which we can apply a good architecture. Now, is architecture fixed? When you initially decide what shape the system is going to be, is that the shape that the system will be? And the answer to that is no. Because as you begin to write the individual lines of code, and as you begin to assemble the modules in that system, you will find that there are pressures created by those modules and by those lines of code that impinge upon the architecture and cause it to change shape. And this changing shape of the architecture continues every time someone adds a new feature or asks for a change to a feature or adds a new facility to the system. That puts pressure on the architecture, and the architecture must respond. Therefore, the architecture is a living, breathing thing. It changes with the system on a day-to-day basis. It is not some fixed map that we all follow for the next 10 years. It's going to be something that we always have to adjust and tweak and twiddle and respond to throughout the lifetime of any software project. Ooh, that was a good rant. I liked that one. So, can I have my slides? Ah, thank you. Good. Oh, I should probably do this to it. Excellent. I've built a lot of applications over the years. I've been writing software since, well, I wrote my first line of code when I was 12 years old, and that would have been in 1964. It wasn't a line of code, though. My mother had purchased for me, at the age of 12, a little plastic computer. She knew my interest in science at the time, and she thought that this would be an interesting scientific toy to give her son. So she bought this little plastic computer. She had no idea what it was. The little plastic computer had 3 flip-flops, little sliding bits of plastic that could slide between 2 states, 3 bits. And they had a little label on the side, 0 and 1, that would show through a window. So I could see the ones and zeros, the 3 ones and zeros, in this little window as I moved the sliders back and forth. The sliders had grooves in them, and those grooves would allow rods, little metal rods, to slip into the grooves. little metal rods had springs on them that would pull them into the grooves, and then those little metal rods would push on other rods that would cause the flip-flops to change state. The rods were coupled to the flip-flops by little tubes that looked like little segments of a soda straw that you would put on pegs on the flip-flops, on the little sliders. If you think about this for any length of time, you'll realize that this is a 3-bit finite state machine, driven by these little metal rods, which were AND gates, and there were 6 of them. So it's a 3-bit finite state machine driven by 6 AND gates. And you could couple those 6 AND gates to the set or reset of any of the 3 flip-flops. At the age of 12, I got this little toy, and I played with it. I opened up the manual. I read the experiments in the manual. They told me where to put the tubes on the pegs and how to crank the machine. And you could make it do some very basic things. For example, you could make it count. If you put the tubes on the pegs just the right way, it would count in binary from 0 up to 7 and then back to 0 again. There was another program that would make it count in reverse order. And the arrangement of the tubes on the pegs was eerily similar but oddly different. And to the 12-year-old mind, I stared at them and went, why are they the same and why are they different? You could make it add. There was an arrangement of tubes on the pegs that created a full adder. So you could put 2 bits in and add the 2 bits, and it would create a sum bit, and it would also give you the carry bit by changing one of the inputs. There were a number of other experiments you could run, about 20 or so. And I did them all, and I was deeply frustrated. Because after all 20 of those experiments, I had no idea how this machine worked. And I wanted to make it do what I wanted to do. And I had a program in mind. It was called Mr. Patterson's Computerized Gate. I wanted this program to execute on this little computer, but I didn't know how to arrange the tubes on the pegs. The connection hadn't been made. At the end of the manual, there was a little paragraph. The paragraph said, if you'd like the advanced programming manual, send in $1 and we will ship you the advanced programming manual. So I did. I got $1 and I stuck it in an envelope and I sent it off. It took 6 weeks because there was no Amazon in those days. But 6 weeks later, in the mail, I got a little packet. In that packet was the advanced programming manual. I keep this in a Ziploc bag on a bookshelf in my office. It holds a place of honor there. I got it down and read it several years ago. It is perhaps the most cogent description of Boolean algebra written for a 12-year-old that is possible to write. It is only about 25 or 30 pages long, but it's completely unapologetic. It assumes that you're curious enough to work. And it starts out immediately with truth tables and Venn diagrams and Carnot maps and goes right into Boolean variables, and, or, XOR, and over, or, X over, or, Boolean algebra like De Morgan's theorem, the associative property of and, the associative property of or, distributive property of and over or, and or over and all that stuff. And I'm reading through it going, yes, yes, I understand, yes, yes, I understand, get to the point. And after they've done all of this Boolean algebra tutorial, within about 12 pages, they say, all right, now, you've got an idea for a program. Here's what you have to do. You have to write down the bit transitions. How are the bits going to change on this machine? Convert that into Boolean equations in and over or form. Reduce those Boolean equations to lowest terms by using the Boolean algebra techniques we gave you. You should wind up with 6 or fewer 3-bit equations. Then here is the little map that shows you how to take those 3-bit equations and turn them into tubes on the pegs. So now I got my little program out, Mr. Patterson's Computerized Gate. And I wrote down the bit transitions. And I converted them into Boolean equations in and over or form. And I reduced them to lowest terms using the Boolean algebra they had taught me. And I put the tubes on the pegs. And I cycled the machine. And that machine did exactly what I wanted it to do. And I was a programmer. That was it. The conversion had happened. The hook had been set. I was going to be a programmer for the rest of my life. I made that decision at the age of 12. And that's what I wanted to do for the rest of my life, and that's what I have done for the rest of my life. At some point, you probably made that decision too. And maybe it was not as dramatic as that, maybe it wasn't a moment, although I imagine that many of you did have a moment like that. At some point, you touched a computer, and the computer did what you wanted. You made it do what you wanted it to do, and you realized that you were a god. A small god in a very small world. But inside that world, you were a god. And you could make that machine do anything it was possible to make that machine do. And some of you probably had that feeling, the same feeling I had, and thought, yeah, this is what I want to do. I had some kind of personality defect, probably. But I believe most programmers are infected with that particular moment in time when they decided, yeah, I want to be a programming god. I've built lots of applications over the years since then, lots and lots and lots of them, and they range from all different kinds of applications. I've done a lot of work in embedded real-time systems. I did a fair bit of work in telephony. I did a lot of machine control applications. I've done financial applications. I've done factory automation applications. I've written tons and tons of code in languages all over the place. And I discovered something. In all those years of writing code and writing applications, and what I discovered was that the rules of architecture are independent of every other variable. The rules of software structure are the same, no matter what the application is, no matter what the environment is, no matter what the language is. The rules of software architecture remain the same. Yesterday, I talked about how software itself has not actually changed much. Sequence, selection, iteration, the fundamental building blocks of software. But it also remains true that the fundamental rules of architecture, of software system architecture, have not changed since the earliest days. They remain stable. Many software developers get caught in the trap that something new is better. Be careful of this one, because there's not much new. One of the things that's new right now is microservices, and everybody is spinning about microservices. Yay, yay, microservices. You realize that microservices were invented within the first 5 years of software development. That the initial Fortran compiler on a 708 computer, the IBM 708 computer, was a set of microservices because they simply didn't have enough memory space in the machine to hold the whole compiler. So they had to shuttle little bits of it in and out, and they had to communicate through a simple protocol, just like a bunch of isolated microservices. Old idea, been around the block a whole bunch of times. It gets reintroduced every 10 years as something new, and everybody spins for a while, and then we realize, oh yeah, that was what we did 10 years ago, and why did we get so excited about it? Be careful of this stuff. The world of software development is a world that at its foundation is fundamentally stable, composed of rules that have not really changed in 70 years, and yet it's driven by this massive effort of popularity, this wild fashion sense. And we wind up with the new fashion of software every year, and the new language every year, and the new platform every year, and the new framework every year, and everybody goes, yes, it's the new thing, and the new thing is not new. It's old. It's the same. And you begin to realize that after, 50 years, I suppose. I told you this yesterday, that getting software working is the easy part. Getting software right is the hard part. But there's magic that happens when you get the software right. And it's magic that very few of us have experienced, because much of the software in the world is not right. But I've experienced it Several others have experienced it. There's this magic that occurs when the software is right. And that magic is that the effort to build it and the effort to maintain it is minimized. The struggle to continue to add to it is minimized. The functionality and the flexibility of the software is maximized. Now, some of you think I'm talking in utopian terms. Some of you think I'm preaching heaven, and only if you don't sin anymore, you will achieve heaven. That's not what I'm talking about here. If you are disciplined, and if you build software with good architecture and a good structure, you will experience a reduction in the effort to keep that software system working. What is design and architecture? Why do we talk about these things in two different terms? Why do we talk about software design and then separately talk about software architecture? Why is this whole day about architecture? And the answer to that is that there's very little difference between them at all. Software design and software architecture are roughly the same thing. We try to push architecture to a higher level because it sounds auspicious. You know, architecture, that sounds high level, and design sounds medium level, but there's actually no line. You cannot draw a line between architecture and design and say, well, this is where architecture begins and this is where design ends. Because even at the very bottom level, there's a little bit of architecture going on, and even at the very top level, there's a little bit of design going on. It's a continuum. And so all of us software developers, are architects. What is the goal of software architecture? Some folks would say, well, the goal of software architecture is to build systems that work and can scale, and there's a whole bunch of things that you could say. But the actual goal of software architecture, the goal of a software architect, is to minimize the human resources required to build and maintain software systems. Somewhere up there it says it's all about people. Yes, it's all about people. Minimize the manpower required to build and maintain software systems. That is the goal of architecture, and that is the goal of the software architect. The measure of design quality is simply the measure of effort required to meet the needs of the customer. The quality of the design can be measured by measuring the amount of effort it takes to meet the needs of the customer. If effort remains constant or shrinks with time, then the design is good. But if the effort required to maintain a system grows with time, then the design and the architecture are bad. It's a very simple relationship. As effort increases, design quality decreases. It's an inverse proportional relationship, and it's very simple to understand. It's also simple to recognize. If you know you are working on a system where the effort has increased, you know the design and architecture are bad. The data that I'm going to present you is real. Unfortunately, it's also anecdotal because I cannot quote the sources, because the folks who want to, the source of the data wants to keep their identity private. Also, it's secondhand, because this data was not collected by me, it was collected by Jason Gorman. But let me present it to you anyway, and you can assess whether or not it's appropriate. This is a case study of a fairly large company that began as a small internet startup and then grew. And of course, that's the hope of all internet startups. They want to grow and they want to succeed. Take a look at the graph on the left there. That's the amount of engineering staff, the number of programmers in the organization. And notice how it's growing at an exponential rate. The numbers on the bottom are the releases. So release 1 had, maybe 10 programmers, 20 programmers, something like that. By release 2, it had doubled, perhaps. By release 3, it had doubled again, and it continues to double, roughly, until by the release 8, they had 1,200 programmers. From 10 to 1,200 in 8 releases. think of the amount of effort that implies. A tremendous amount of increased effort. Why? To get to the next release. What's going wrong there? The amount of effort applied to this application is growing exponentially, which tells you that the design and architecture are crap because the effort is growing through the roof. Take a look at the graph on the right, the blue one. That's the number of lines of code in thousands from one release to the next. And notice that it has the inverse relationship to the effort. The effort is an exponential scale. The number of lines of code is a logarithmic scale. The number of lines of code is not changing much. Even though there's 1,200 programmers, the amount of new lines of code are vanishingly small. If you're an accountant and you're thinking in terms of money, that would scare the hell out of you. If you're the CFO of this organization, that would look like a disaster in the making because you're spending immense amounts of money and you're getting almost no return. Take a look at the financial signature of the bottom. On the bottom, this is just the cost per line of code in programmer salary, and it's following the exponential curve. The cost per line of code is going through the roof. Something has gone wrong here. Now, what is it that went wrong? Well, it's an internet startup. And internet startups, do you think they follow any design and architecture rules? Or do they just kind of throw a bunch of code together and hope that something great happens? And in most cases, it's the latter. So the startup culture, especially in the United States and particularly in the West in general, the startup culture is a culture of making a mess as fast as you can in hopes that you can produce something that will put you on the exponential growth of profit. But this is a very bad strategy, even for an internet startup, because it forces most internet startups to experience this particular problem, and before they can ever get profitable, it kills the company. Most internet startups, especially software internet startups, fail not because they couldn't have succeeded commercially, but because they can't maintain and sustain the cost of the software they're producing. We all get excited about, Facebook or other internet startups that really made it big, but how many fail that you never hear of? And the numbers are astounding. Massive numbers of them fail. Would they have failed if they had kept their software clean? Some of them would have. Many probably would not, because they could sustain the effort long enough to grab onto the profit roller coaster. Some people worry that, well, we've got to be first. That's the only way to grab onto the profit roller coaster is to be first, and therefore it's justified that we make a mess early so that we can grab onto the profit roller coaster, and then we will be able to afford to clean up the mess later. Was Facebook first? Not by a long shot. Facebook wasn't first. Facebook wasn't second. Facebook wasn't third. There were a whole bunch of social networking companies out there. Facebook just happened to hit for some reason, and it's not exactly clear why. Whatever happened to MySpace? Was anybody on MySpace? Oh, yeah. What happened? Just didn't hit. For some reason, didn't hit. They did something wrong, but it wasn't because they got there first. Facebook succeeded, not because they got there first. Continuing on with this, look at the productivity per release. The productivity per release, I arbitrarily set to 100% at release 1. By release 8, the productivity is on the floor. I told you about this yesterday, the decline in software productivity as the mess builds. Here's the actual measured evidence. And look at that fascinating curve, how it dives so rapidly and then bottoms out and asymptotically approaches zero. Once again, I stress, this is real data. And look at the cost per release in monthly payroll. If you're the CFO, and that's who that guy is there, well, it's not really him. I just found that picture online. But I think it probably assesses pretty well his attitude towards what's going on here. There's an old fable of the tortoise and the hare. It's one of Aesop's fables. And the fable goes this way. There's a rabbit, a hare, a rabbit, who can run fast, and a tortoise who goes slow, and they go into a race. And the rabbit is so confident that he can win the race because he's fast that he falls asleep, and the tortoise passes him and wins. And the moral of the story, of course, is that slow and steady wins the race. Have you ever heard that adage? Your grandmother probably told it to you. At least, I don't know what it is in Dutch, but in English, that's what it is. Slow and steady wins the race. One of the things that we face in the software community right now is this issue of the hare and the tortoise. Because everybody wants to be the hare, running as fast as they can to produce softwares as quickly as they can. And we hear the effort from our organizations. We have to go faster. We have to go faster. We have to go faster. And every software developer in the room has heard that message. We have to go faster. And you feel the pressure. You judge your self-worth by how fast you can go. That is not your self-worth. That is not your worth as a programmer. Speed is not your worth as a programmer. But we judge it that way. We think that way. That's how it's been impacted upon us for decades. Speed is everything. And so what happens because of that speed? Because of that need for speed, we become overconfident, like the hare. But what is the overconfidence? The overconfidence is not the confidence that we can go fast. The overconfidence is the confidence that we can deal with the mess. Okay, we're going to go fast, but we can deal with the mess, and we'll go back and we'll clean it up later. We'll deal with it. We'll deal with it somehow. We can deal with the mess because we need to go fast, and so we roar down the track, and we're going really fast, and we're making a mess, and the overconfidence is that we can deal with that. And what is the tortoise in this scenario? The tortoise is the mess, because the mess builds slowly but inexorably. And eventually it will pass you and dominate everything about the project. Of course, we need to go fast. But how do you go fast? What's the secret to going fast? Is it typing faster? Is it thinking faster? What is the secret to going fast? The secret to going fast is to not build the roadblocks that are going to make you go slow. Because the roadblocks will make you go slow. So don't build them. You're a programmer. How fast can you go? Well, you have a speed. It's your speed. It's nobody else's speed. It's just yours. It's the speed of your thought, the speed of your ideas, the speed of your ability to conceptualize. Is there anything you can do to make that go faster? Can you rewire your brain to make yourself go faster? Well, yeah, there are some things you can do. Study, practice, but they're long-term things. They're not short-term things. If someone comes to you and says, I need you to go faster, what can you do? What can you do to go faster tomorrow? Nothing. Nothing. There's nothing you can do to go faster tomorrow. You might be able to go faster next year by learning something, by studying something. You might be able to go faster 5 years from now by practicing and developing skills, but there's nothing you can do to go faster tomorrow. So what's the key to speed? You cannot speed up. What is the key to speed? And the key to speed is not to slow down, not to build the stuff that's going to slow you down. So the key to going fast is to go well. Do the best job you can. Do the cleanest job you can. Make sure the track is nice and clear. Don't roar down and throw a mess down there. Build in a steady, consistent, clean way so that you can continue to go as fast as possible. Which, by the way, may not be very fast. But at least it's not going to slow down. We often have the impression that going clean is slow. And so we make the decision that temporarily we will go dirty because we can go faster by going dirty. Many, many people think that. In fact, there is a phrase in English, I don't know if you have it in Dutch, and the phrase in English is quick and dirty. Now, there's no such thing as quick and dirty, at least not in software. You cannot go fast by making a mess, even in the short term. And this is one of the debates we will have. Some folks will say, well, I understand that a mess will slow me down in the long term, but in the short term, I can go faster by making a mess. No, you can't. No, you can't. The mess will slow you down within an hour or two. How many of you have had the experience that you write code on your screen all morning long, you go to lunch, you come back from lunch, you look at your screen and said, who the hell wrote that crap? Because the mess will slow you down in a matter of an hour or two. If you are not clean, the mess builds and slows you down instantly. The graph that I'm showing here is from the same guy. Jason Gorman did this experiment, and I thought it was a good experiment. He wrote the same program 6 times in a row on 6 different days. The program he wrote was a program that he knew very well. It's an exercise that programmers often use as a way to practice. It is the conversion of an integer into Roman numerals. Try this one day. It's a fun little program to write. What he did is he wrote a set of acceptance tests that would demonstrate to him when he was done, prove when he was done. And then he set about to write that program 6 times in 6 different days. But on every other day, he used a discipline. On the even days, he did not use the discipline. On the odd days, he did use the discipline. The discipline was test-driven development. And you can see the results here. Now, notice the bottom of the graph, right? This is one of those statistical cheating mechanisms, right? I cut the bottom of the graph off at 22. So what we're talking about here, the differences here are relatively small, but I wanted to accentuate them, so I'm lying with statistics. With test-driven development, he was always faster. Notice that he's always getting faster during the entire exercise, right? Every day he does it a little bit faster than the day before. But with test-driven development, he was always faster than without test-driven development. And yet his experience was that test-driven development felt slower. And why did test-driven development feel slower? Well, any discipline feels slow. All disciplines feel slow because when you are exercising a discipline, you are stepping through the discipline one step at a time. All disciplines feel slow, but they speed you up if they're good disciplines. Test-driven development is a good discipline. Sped him up every time. Just felt slow. What is the solution to the executive's dilemma, the dilemma that the effort is building exponentially and the return is falling off logarithmically? What is the solution to this? And the only way to reverse the decline in a software project is to just be as clean as you possibly can. That all the developers and all the architects and all the designers follow the disciplines of software development and write the best code they can all the time. And the executives and the managers need to set that expectation. What do we, as managers, expect from programmers? We expect you to do a good job. And we trust that if you do a good job, you will be going as fast as possible. That is the expectation of management, and that is the behavior required of the software developers. Software has 2 values. There's the value of what it does, and there's the value of its structure. Programmers often ignore the second value. We focus on what the software has to do, and we believe that our job is to satisfy that need. There's a set of requirements out there, And we must meet those requirements. And if we meet those requirements, we have done our job. But if we do that, we have only satisfied the first value of software. There is a second value of software, and it is arguably the more valuable of the two. The second value of software is software that actually works when you make it work, you stupid thing. Yeah. There it is. Look at that. Dumb thing. The second value of software is the structure of that software. And why is that a value? It's a value because of what software is. Yesterday I told you that software is a compound word, that it means flexible product. Software, the very nature of software is that it must be changed. It must be changeable. If it is not changeable, the software has no value. If you give me a system that works perfectly now, but I cannot change it, that software will be worthless tomorrow because the requirements will change. And if I can't change the software, that software will become worthless instantly. So that I must be able to change it. I must be able to modify it. And the cost of modifying it must be low so that I can continue to make that software do what it needs to do to satisfy the customer's demands. If you give me software that does not work, but it's changeable, I can make it work. It is more important that the second value be maximized than the first. Because if the second value is maximized, if the software is flexible, I can make it work. But if you maximize the first value at the expense of the second, if you maximize the fact that it works today at the expense of being able to change it, then when the requirements change, the costs will inhibit that change. And if they inhibit the change too much, the software project will fail. These two values are necessary for every software developer to keep in their mind at all times. It is not enough to make the software work. The software also has to be right. And the word right is an unfortunate word because it's a binary word. I don't need the binary connotation. The software has to be well structured, but it doesn't have to be perfectly right. It has to be good software. It has to be well thought through. The structure has to be changeable. The value of its structure has to be high. Now, let's see if I can make this stupid software work. By the way, just a little rant. Are we going to see self-driving cars anytime soon? Oh, yes, we have. We've seen some. They haven't killed too many people yet. They drive in relatively safe areas during good weather, and generally the law says that there has to be an actual person in them to take over. We don't typically see autonomous cars running without a human in them, although there have been a few cases of that as well. But my question is not that. My question is, are we going to see self-driving cars that you and I can go to Uber and call one up, and a car will pull into our driveway without a driver in it, and we will tell the car to take us somewhere, anywhere, and the car will take us anywhere, drop us off? Are we going to see that? No, not a chance. Not a chance. This is an overconfidence in software. Software is not that good, as I just demonstrated with that stupid program right there. Software is not that good. We're not going to see that in 2 years. We're not going to see that in 5. I don't think we'll see it in 20. We may not see it in 50. And there's a number of reasons for that. We've all gotten extremely used to the idea that software, computers, are an exponentially growing thing. Who remembers Moore's Law? Yeah, okay, so Moore's Law is dead. Right, Moore's Law died over 10 years ago now. Clock rates on computers have not increased since about 2002. Right? My laptop in my bag over there goes at 2.6 gigahertz. The laptop before that went at 2.6 gigahertz. The one before that went at 2.6 gigahertz. And it wasn't until I can get back about 10 years that one was maximized out at about 1 gigahertz. Clock rates have not increased. We've tried to increase their productivity or their throughput by adding more processors. So about 10 years ago, I got my first 2-core processor, and then I got a 4-core processor. I was convinced that the next laptop I was going to get would be an 8-core processor, but that did not happen. And then I thought, well, certainly the next one after that will be an 8-core processor, but that did not happen, and I don't believe it will now. I don't think we're going to get 8 cores. Maybe we will, but I don't think we're on that power of 2 curve. The density of the chips can't get much greater because the number of atoms in a wire is now countable on a hand or two. So it's gotten to the point where we can't really get much more density. We may be able to go in 3 dimensions, but the heat problems there are maybe insurmountable. The point I'm making is that the hardware that we have been used to growing at an exponential rate is no longer growing at an exponential rate. We are sitting now on a plateau. Computer power is probably plateaued. We can enhance it a bit by going up to the cloud, although there's costs to the cloud. Don't just say that the cloud is great and wonderful and everything is life is great on the cloud, because the cloud has a whole bunch of costs to it. But we can certainly gain more computer power by recruiting more and more servers on the cloud, but all we're doing is recruiting more and more servers, and that, by the way, is a linear growth, not an exponential growth. So we've got this problem. Our expectations of exponential growth have set us to believe that in 10 years, virtually anything's possible. Anybody read, the singularity that's coming? What was that Kurzweil wrote about the singularity? Eventually machines will be able to design better machines, and they'll design better machines, and the whole thing will roar off into some apocalypse. No, that's not going to happen. Who heard about Watson? Right? Who won Jeopardy? Right? The IBM computer that won at Jeopardy, beat all the best Jeopardy humans. And that was a great achievement. It's a wonderful thing. But let me tell you about one question that Watson got wrong. And the question that Watson got wrong was, name a city that has 2 airports, one named for a World War II hero and the other named for a World War II battle. Now, the answer is Chicago, because O'Hare Airport is named after Butch O'Hare, who was a World War II hero, and Midway Airport, the other airport in Chicago, is named after the Battle of Midway. So the answer is Chicago. Watson said Toronto. Now the question was, name an American city, and the answer was Toronto. Now Toronto is in Canada. I suppose that's American. It is the 51st state. In Canada, that joke doesn't go over so well. But Toronto does not have 2 airports that meet that criteria. So that's clearly wrong, and besides, it's not an American city. And when the programmers dug into it to find out why, and notice that the programmers had to dig into it to find out why Watson answered Toronto, they found that there was a city in Idaho named Toronto, which happened to have 2 airports near it, and they matched the 2 criteria. So Watson was correct, although stupid, worse than stupid, irrational. No human being would have answered that question that way. And if any human being had answered that question that way, we would have sent them to a mental hospital. Because that makes no sense in human terms. Chicago is the obvious answer here, not Toronto, Ohio, Idaho. Now imagine a self-driving car. And the self-driving car, during a rainstorm, runs over a 2-year-old. Kills him. Who goes to court over this? Who should we blame for that? Someone must be responsible. The 2-year-old is dead. Someone has to be held responsible. Who do we blame? The car? The programmers. The company that made the car. Is there anybody who can take responsibility? Let's put the car on the stand. Let's interrogate the car. Car, why did you kill the 2-year-old? Toronto. Yes, I told you about that. Yes, I told you about that. Stakeholders in software systems believe that requirements and changes are complicated only by scope. Now, a stakeholder can understand that certain changes are big and that other changes are small. And they believe that the cost of changes will be proportional to that scope. Big change, it should cost a lot. Little change should cost a little. But programmers don't see it that way. What happens is that programmers will build structures in their systems. And what a stakeholder believes to be a small change will cause massive repercussions through the structure of the software. And so the developer looks at that as a big change. This is a faulty architecture. A faulty architecture is an architecture that lies to the stakeholders by making small changes expensive and big changes cheap. Programmers see each new requirement as a puzzle piece that must somehow be fit into the existing puzzle of the software. And the more puzzle pieces there are, the less room there is in the puzzle for a new puzzle piece. And the software developers are constantly struggling about how the heck are we going to fit this doggone thing in here, and so every new change gets more and more expensive. The solution to this is to keep that puzzle as simple as you can keep it. Keep all the edges square. All the pieces as nice squares, so that you don't have this problem of trying to fit everything in there all the time. Yes, I told you that already. Stakeholders want changes, but stakeholders do not have the ability to prioritize architecture. They don't know what architecture is. They don't know what software design is. Stakeholders in a system have no clue that you have to work hard to build a structure that supports their requirements. All the stakeholders see are the requirements themselves. They don't see that structure, that second value. They cannot assess the second value, and therefore they cannot prioritize it. No stakeholder can prioritize architecture. And it is improper to expect that stakeholders will prioritize architecture. Software developers are very often complaining about the fact that nobody ever prioritizes architecture. All they care about is requirements. Well, of course. All they care about is requirements because that's all they know. They can't understand what architecture is. You know what architecture is. You are the only ones who know what architecture is. And it is your responsibility to communicate that as forcefully as you can to the stakeholders in the system. And that puts a very interesting responsibility on you and I. We have to somehow communicate the importance of the second value to the people who are paying us. And if we fail at that, the people who are paying us will pay way too much. For their sake, we have to communicate the importance of the second value. I like to look at it slightly differently. I like to say, the stakeholders of a system have no right to tell me what the architecture ought to be. They have no right to come into me and say, skip the architecture, let's just get this done fast. They have no right to say that to me, because I know how to get this job done well. You do too. You know how to do the job well. We all do. We all know how to go well. We know how to do it. Stakeholders don't have the right to say, oh, no, skip that. Don't do those disciplines. It's too slow. They don't know it's too slow. They're just guessing it's too slow, maybe for some reason. You know. And you have the responsibility to communicate that backwards. Back down. And how do you do that? By asserting your authority. Because you have the authority. You have the authority because you have the knowledge. You have the authority because you have the responsibility. Believe me, you know who's going to get blamed. So you have the responsibility and you have the authority. You must communicate that downwards. That is not an easy thing to do. Communicating that importance to people who are interested in requirements is not an easy thing to do. It requires a certain amount of emotional fortitude. And programmers, and I'm sorry for this stereotype, but it tends to be generally true, programmers did not get into programming because they like dealing with people. Programmers would rather, most of them, and not all of them, but a large percentage of programmers are perfectly happy sitting at a terminal, locked in, coding away, and people are an annoyance. Especially if those people are emotionally confrontational. I learned something a very long time ago. And it's a generalization that I will make here. I don't have any research to say that it's true, but I believe it's true just from my own experience. There are people like programmers who like to deal with things, like code, but there are other people whose greatest joy is dealing with other people. Now, that's not something I understand. Right? Because although here I am sitting on stage, right, and I'm pretty good on stage, being on stage is a formula. It's an algorithm. I can execute that algorithm, and I can execute it very well. I do not actually have to relate to you. Isn't that interesting? For all intents and purposes, I'm not going to say what I'm about to say. What I'll say is this. I can do this on stage if you weren't here. I could be on stage alone with a camera there, and I could be exactly the same. And some of you have seen me do that. Right? Programmers, like me anyway, are not very good at emotional confrontation. But I learned something a long time ago. There are people who are good at emotional confrontation. They're good at it. They've developed the skill. And it's a people skill. And it's not just emotional confrontation, it's relating emotionally to people. I'm not good at that, but they are. They get their joy out of it. And very often they become salespeople and managers. How do people like that get the truth? I know how I get the truth. I get the truth mathematically and logically. I think it through. You know, it's a cold thing. Truth for me is cold. But I believe for them, truth is hot. They get the truth by testing people. They want to know what you believe. And so they will confront you. And they will say to you, you don't really believe that. I need this by then. I need this to happen this way. And they will confront you. And they want the truth. They're seeking for the truth. And if you go, oh, okay, they got a truth, but it's not the truth. I learned this by sitting in a conference room with a bunch of managers. And we had a real problem at this company, and we had a bunch of customers. There was no way to satisfy all these customers. We were going to have to let some of them down. There was the customers that I was representing as an engineer. There was customers that other people were representing. We were having this discussion. I saw the discussion going away from my customer. And here I am sitting there, you know, little Bob as a programmer, watching these guys take the resources away from the customer that I was supposed to defend. And I completely lost it. I started yelling at them, right? Which is very uncharacteristic for me, despite what you see on stage. And I looked them in the eye, and I yelled at them, and I used flowery language. Do you beg the lightning to strike? Which I stole from Star Trek, by the way. And I saw these managers look me back in the eye with a respect I had never seen in their eyes before. And suddenly they accepted my assertions and said, yeah, you're probably right about that. We're going to have to do something a little different. We've got to pay some attention to that customer. That had never happened to me before. I'm not sure it's happened ever since, but that was a fascinating lesson for me. that there are folks, and they tend to be the folks who are managers and salespeople and people, who learn the truth through confrontation. And so you and I, who are the defenders of the architecture, the defenders of their money, need to learn how to tell them the truth. And that is not an easy thing. Now, by the way, I'm not telling all the junior people in the room to rant and rave and scream. But it might be wise for the senior people in the room to learn the skills, as distasteful as they are to a programmer, of dealing with people. Because it's about people, isn't it? This is Eisenhower. General Dwight D. Eisenhower, the general of the victory in World War II. Then he became president of the United States. And interestingly enough, Eisenhower was not convinced whether he wanted to run as a Republican or a Democrat. This was at a time in the United States when you could barely tell the difference between the two parties. That has changed. And Eisenhower said this very famous statement. Where's the statement? Previous slide, yeah, thank you. You all read it before me, right? So, yes, okay, good. I have two kinds of problems, the urgent and the important. The urgent are not important, and the important are not urgent. These two kinds of problems are the two values, the urgent and the important. The requirements are urgent. The architecture is important. The architecture is important because it has an extremely long-term value. The requirements are urgent because they have a short-term value. They need to be implemented soon, otherwise the customers will be unhappy. The architecture is important. And then Eisenhower put this matrix together. Which of these are you going to do? The important and the urgent, the important not urgent, the unimportant and urgent, or the unimportant not urgent? I would make the case that the one on the lower right you're not going to ever do. It's unimportant, not urgent. What about the unimportant, urgent things? You might not do those. If you have some time, you might do them, but you might not do those because they're not important. They're urgent, but a lot of urgent things can be waved away and say, sorry, can't do that one. I know it's urgent, but it's not important. And then there's, of course, the important, urgent ones. You're going to do those. You just have to do those. And then there's the important but not urgent things. And this is where we get into the biggest debate. And as defenders of the architecture and defenders of their money, those are the ones that we fight over. And we'd better win those. It's always a struggle. These things aren't easy. It gets into an area the programmers don't like to get into, this whole interpersonal thing. But you have to remember something important. You are a stakeholder too. There are stakeholders that aren't programmers, but every programmer is a stakeholder because your reputations, your jobs, your salaries depend on the job that you do. You have a stake in this. So you are also stakeholders, no less than any of the others, and you have a say. If architecture comes last, the costs will grow, and the costs to the organization and the costs to you may grow insurmountably. That was the talk I was supposed to do second, because that was the architecture of the software crisis. But I thought it would be better to do that one first. Are there any questions about that? Before we go on to the next one, which is clean architecture. That was a little more technical. So all the people in the room go, oh God, thank you. Stop talking about all this people shit. Okay? Questions? Comments? Good, okay. Clean architecture. Bum, 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 bum. No, wrong one. Wrong one, no. That one, there we go. Okay, so now we're going to get techie, but no less significant. About 8 years ago, my son handed me the source code of a project. And I opened it up, and this is what I saw. Now, this was a Rails project. Has anybody here done any Ruby on Rails? Oh, yeah, okay, a few of you. Good, good. Well, then you'd recognize this as the directory structure of a Rails application, because all Rails applications have roughly the same structure. This is Rails of about, I don't know, 6, 7 years ago, something like that. And I looked at it, and I said, oh, yeah, it's a Rails application. I can tell by the directory structure. I had seen lots of other Rails applications before, and I knew what the directory structure was, so it was very familiar to me. But that moment, for some reason, struck me as odd. It had never struck me odd before, but it struck me odd this time that I could look at the directory structure at the top level of the application and realize that it was a Rails application. Now, why is that at the top level of the application? Oddly, what I could not tell from the top level of the application is what the application did. And that bothered me. I thought, wait. At the top level, shouldn't I be seeing the intent of the application? Why am I seeing the framework at the top level? And that bothered me. It had not bothered me previously, but it bothered me on that day. And so I started to think about this. And I thought, well, now wait a minute. Rails is a web framework. And what is the web? The web is an I/O device. Has anybody thought about it like that? The web is an I/O device. Now, maybe you think it's a really complicated I/O device and a really cool I/O device, but it's an I/O device. It's on the outside of our system. It's peripheral to the system. It is a peripheral device. And there's something we learned a long time ago about I/O devices. We learned this way back in the 60s. We don't want to know they exist. We build operating systems to hide I/O devices from us. Who's done some Unix work? Right? Standard in and standard out. What device is that? Huh? We don't care. We don't want to know. Why don't we want to know? Well, long ago, back in the 50s and the early 60s, people would ask us to write programs like, can you write a payroll program? And we'd say, yeah, we'll write you a payroll program. You just punch all the employees onto cards, and we'll read them in, and punch their time cards onto cards. We'll read them in, and we'll punch out paychecks. And we'd write the code that way, and the code would literally talk to the card reader and the card punch. And then they'd come along 5 years later and say, you know, we moved all our records onto magnetic tape, and the programmers are going, oh my God, that changes everything. Because dealing with the tape driver was really different from dealing with the card reader and the card punch. And we thought, okay, we don't want to go through that again, so let's just make all the I/O devices below the level of the operating system. The operating system was invented primarily for this purpose. Let's get all the I/O devices below some line, some boundary line, and then we can write our code and never worry about that again. And here I've got the web at the top level of the application. The web dominates it. The I/O device dominates. I thought, well, that's wrong. There's something wrong with that. Architecturally, there is something wrong with that. So I started looking around at floor plans of buildings. And I noticed that the floor plans of buildings do not tell me what the buildings are made of. The architecture of the building does not tell me that the building is made of bricks or wood. It doesn't tell me about hammers and nails. What the shape of the building tells me is the intent of the building. That's a library. And you can tell it's a library. If you look at it for any length of time, you'll say, oh, it looks something like a library. It's got rooms, it's got tables, it's got like library stuff. And if that doesn't convince you, this one will. That's a church. The architecture of buildings screams out the intent of the building. The shape of the building tells you what the intention of the building is, how it's going to be used. And isn't that what the architecture of a software application should be doing? Shouldn't the architecture at the topmost level be screaming at you about what the intent of this application is? It's a banking application. It's a payroll application. Shouldn't it be yelling that at you? Instead of saying, I'm a Rails web app. Who cares if you're a Rails web app? I don't care if you're a Rails web app. I want to know what you do. And that made me remember something. It made me remember this. The guy you're seeing is Ivar Jakobsen. He wrote a book in 1992. The name of that book was Object-Oriented Software Engineering, and the subtitle was A Use Case-Driven Approach. Does anybody remember use cases? There's a little Led Zeppelin there. Anybody remember laughter? Nah, none gets that joke. Does anybody remember use cases? Yeah, a bunch of you remember. And what happened to use cases? The consultants got at them. And the consultant said, oh, use cases, people like use cases. Okay, well, then I need to be the use case expert, and so I'm going to put something on the web that lets people fill out a form for use cases. And then the next consultant said, well, I can do that too, but my form's going to be better. And there was this war about the best possible use case form, and by the end, there were these crazy forms on the web, on the internet, it wasn't the web at the time, and they were full of all kinds of blanks you could fill in, what's the primary actor and the secondary actor and the tertiary actor and the preconditions and the postconditions and all this crap. And the world kind of went, maybe we don't want to know about use cases. That was right about the time that Agile started. And Agile said, we got to rename this thing. So they named it User Story. Same thing, though. When Jakobsen was talking about, we're not massive forms filled out with lots of detail. A Jakobsonian use case, well, it looks like this. This is a Jakobsonian use case. And assume that this is for a system, an order entry system, for example, and this is the create order use case. And notice that it does have a little bit of structure in it. It identifies the input data to the use case. In this case, it's the customer ID and the shipment destination, the payment information. Notice also that there's no detail there. I don't tell you what the customer ID looks like or what the shipment destination looks like or anything like that. The use case is not the place for that detail. We don't put that in there. It's just a list of the kinds of data we think we're going to need in order to execute the use case. And then the next thing down is called the primary course. That's what Jakobsen called it, the primary course. And this is just the processing steps. And in this case, it's the order clerk issues the create order command with the above data. That's actually not part of the use case. That's what kicks the use case off. The system validates all the data. Doesn't say how, doesn't tell you what the validation rules are. No details or anything, just validates the data. System creates the order and determines the order ID. That's probably a database operation, but it doesn't say that here. And then it says that the system will deliver the order ID to the clerk, probably on a web page, but it doesn't say that either. It's a very nice, concise description at an extremely high level of what the input data is, the processing steps are, and the output data. Now, Jakobsen said something very interesting in his book. He said, if you've got a use case in this form, you can turn it into an object. Remember, the title of the book was Object-Oriented Software Engineering. He said, if you've got a use case in this form, you can turn that into an object that you can write code in. And he called that object a control object, but the name didn't work because of model view controller, and everybody got confused, so I renamed it Interactor recently. Other people have chided me for this and said, well, Bob, you should have called it use case, and I think they've probably got a point, but I called it interactor, so I'm going to stick with that for the moment. An interactor object embodies a use case. It's a class that you write in Java. It embodies a use case. It contains application-specific business rules. Now, we need to separate business rules into two different types. There are application-specific business rules, which are all about the automation, and then there are application-independent business rules, which are the business rules you would execute even if there weren't a computer. There's a bank charge interest. That's a business rule that you're going to execute even if there's no computer. The use case is application-specific business rules. They're all about the automation. These are the things you have to do because there is a computer. Now, where do you put the application-independent business rules? Well, Jakobson put those into these things that he called entities. Nowadays, people call them business objects, but I've kept the word entity in honor of Jakobson. These entities are controlled by the interactors. So the use case, the interactor, guides the execution of the entities. It controls the execution of the entities. The entities execute the real business rules. The use cases coordinate the business rules. And then you've got to get some data in and out. And Jakobson called those interface objects. He later changed the name to boundary objects. I have kept that name. And I have drawn them here as Java interfaces. There's two of them. You can see there. The one on the top is the output boundary. And you can see that it's the output boundary by that red arrow that points towards it. In UML, that is a using relationship. So the interactor uses the output boundary to send data out. The boundary on the bottom is the input boundary, and you can tell that because of the red inheritance arrow from the interactor. The interactor actually implements the input boundary interface, and it uses the output boundary interface. The methods on the boundaries are the methods that allow data to come in and data to go out. Now, let's walk through the process here, because the process is pretty simple. We've got some user down there at the bottom, and the user is interacting with the system. And I've got a delivery mechanism there. I purposely called it a delivery mechanism because I didn't want to say web. It's probably the web, but okay. I called it a delivery mechanism. So the user is dealing with probably some web page, filling out some form, and eventually the user hits the submit button, and that passes the data into the delivery mechanism, into the web server. The web server reorganizes that data and creates a data structure, which I've called a request model. This is a raw data structure. It's full of just plain old objects. This request model does not derive from any framework. It doesn't derive from any kind of web-related thing. It does not know anything about the web. It is just the data structure that holds the input data to the interactor. It gets passed through the input boundary to the interactor. The interactor looks at it and interprets it with a bunch of if statements, and then starts to coordinate the dance of the entities. Tells the entities what to do and what data to do it on, feeds the data from the request in. Then, when the entities are done, the interactor reverses the flow and gathers the result data from the entities and builds a result model. The result model is just a raw data structure. It has no notion of the web at all, has no idea how this data is going to be displayed. It's just a plain old Java object if you're using Java. And then that result model gets passed out through the output boundary, through the web, which formats it and does all the interesting stuff and gets displayed back to the user. It's a real simple input, process, output kind of structure. But it has a very interesting aspect to it. Can you test those interactors? Do you need the web server running to test those interactors? No, because the web, you don't need the web. You can go through those boundaries. The whole web doesn't have to be there to test the interactor. You can test the business rule without the web. Now that's good because the web is slow. You can run your tests a lot faster if you can test without the web. It's also a lot easier to test without the web at 30,000 feet. So if you're flying over the Atlantic and you've got your laptop with you and you want to run some tests, well, you can run tests because the web doesn't have to be there. And that's interesting. And how do you do that? Well, you feed a request model in and you make sure that the response model comes out appropriately, and you can test all the business rules without the web being there. You can test everything on your laptop at 30,000 feet. Now, what about Model View Controller? I thought we were all supposed to be doing Model View Controller. Is this somehow related to Model View Controller? The answer to that is, well, yes and no. Where did Model View Controller come from? Does anybody know? What's the history of Model View Controller? Model View Controller is probably the first named design pattern. Before the Design Patterns book was ever written, decades before the Design Patterns book was ever written, the Model View Controller design pattern was well known. It was invented by this guy, whose name I'm going to butcher. He's Danish. His name is Trygve Renskaug, but I've butchered that name because I don't know how to say it. I met him once. I was in Norway at a conference, and I was in the speaker lounge, and I was looking for a place to plug in my laptop. And this old grizzled guy reached down and handed me a power strip. And I took the power strip from him, and I looked up, and, oh, that's Trygve Renskaug. And my hand happened to brush his. And I haven't washed that hand. Trygve Renskaug, back in the 70s, came up with this idea, Model View Controller. It's a very simple idea. There's a model object in the middle. The model object understands business rules. Right? So let's say we're doing a clock. The model will understand how to keep time. It doesn't know how the time is displayed. It doesn't know how input from the time comes. It just knows about time. The controller knows all about input. It gathers input from some input source and then restructures that input into commands against the model. And the view knows how to display the model data somehow, knows how to present it somehow, somewhere. We don't care where. Notice the funny little arrow that I used from the view. That is an observer relationship. An observer relationship involves a callback. The view registers with the model, and then when the model changes, it tells the view, hey, you better redisplay me because I changed. This is Model View Controller. This is the way Model View Controller was invented in the 1970s when in the Smalltalk environment. It's a very simple input, process, output model, and it was intended to be used in the small. You did not have a Model View Controller for a page or a screen. You had a Model View Controller for a button. You had a Model View Controller for a text box. You had a Model View Controller for a little canvas. A screen would have dozens of little Model View Controllers dancing around. That was how we structured it in those days. So this is all changed now. Model View Controller has changed, and it gets changed by people who don't read the original work but hear the words and think, well, Model View Controller, I think I understand that. I don't need to read the paper. So what it has turned into is this, and it's very unfortunate. We've got the web out there, and the web does all the interesting work of gathering input from the user and then turning it into URIs or URLs or God help you, whatever. And then eventually the web hands that off to controllers, and the controller's job is to parse all that input data and then talk to business objects off to the side there. And the business objects do their little dance, and then the controller hands the control over to the views, and the views gather the data from the business objects and display it. And that's how Model View Controller has unfortunately evolved. Now, the problem with this is that there are no hard boundaries here. The controllers know about the business objects intimately. What happens is very often business objects start to accumulate controller-like functions, or worse, controllers start to accumulate business rule-like functions. The same thing happens to the views. The views will often accumulate businessy-like functions, or worse, The business objects will accumulate formatting and display-like functions because the boundaries aren't well formed here. So although model view controller is a nice thing to do when it's done in the small, it starts to falter and fail when it's done in the large. Now we come back to Jakobsen's model, and I've drawn a boundary in here. That double black line is a boundary. And boundaries are going to become very important to us because boundaries are the essence of architecture. That is an architectural boundary there. And notice across that architectural boundary, all dependencies point in one direction. And that direction is towards the business rules. All of that is very important. That's called the dependency rule. Across an architectural boundary, all dependencies point towards the business rules. Now, what do we see here? We see the interactor. The interactor has just created the response model. The response model is going to be passed through the boundary to a presenter. The presenter lives on the other side of the boundary. The presenter implements the output boundary, and it lives on the other side of that double black line. The job of the presenter is to reorganize the data so that it is ready to be displayed. The response model is a raw data structure, but it doesn't know how the data is going to be displayed. So, for example, if there is a date in the response model, it is a date object. If there is currency in the response model, it is a currency object. By the time the presenter grabs it, however, it will transform those objects into strings. So you notice that the presenter creates a view model. The view model is a data structure that contains strings. The dates will all be turned into strings, properly formatted. The currencies will automatically all be turned into strings with the appropriate commas and dollar signs or currency symbols or what have you. If there are menus on the display, the names of those menus will be in the view model. The presenter will load them. If there are buttons on the screen, the names of those buttons will be placed in the view model by the presenter. If a button should be gray because it's inactive, the presenter will set a Boolean in the view model to tell the view to make that button gray. All the interesting decisions about the view are actually done in the presenter and put into this view model data structure. And then the view model data structure is handed to the view, and the view I've drawn is this kind of faded thing because it has almost no code in it. All it does is take the data out of the view model and put it into the display. Can you test that presenter? Can you test it without the web server running? Yes, you can. So half of the view side of things I can test without the web server running. Can I test the view without the web server running? That would be difficult. Can I test the view without the interactor? Yeah, I can. I can test the view without the interactor. That means I can test the view without any business rules. I can just test the view stuff without any business rules. That means that view test is probably going to go fast. This shows the whole left side of the structure. We've got the interactors on the right, and they take in request models, they produce response models, they pass the data through the boundaries. The controllers are the ones that pass the data into the interactors. The presenters are the ones that take the data and present it to the view. And there's that big architectural boundary there, and notice that all of those arrowheads are pointing to the right towards the business rules. That's the dependency rule. What about the database? I'm going to show you a picture. See if you recognize it. Is that the database? Is the database the great God in the center of the system with all the applications around it bowing down before its majesty? Who benefits from that view? Yeah, Oracle does, right? Yeah. Database companies, you know, that's where that view came from. That was a big marketing ploy back in the 70s and 80s to make sure that databases were considered central to everything. And it was fascinating to listen to the marketing language at the time. They coined this term called data assets. What a great term when you're talking to a CEO. You know? Do you protect your data assets? I didn't know I had data assets. Oh, yes, you do. And our system will protect your data assets. Oh, I better buy your system. Yes, you should. Fascinating marketing scheme. It worked wonderful. Just look around and see all the Oracle buildings around, and you'll notice that worked very well. It's a fascinating marketing strategy, but what is a database? It's an I/O device. Databases are I/O devices. They store data. They're little rotating disks. They're the software on top of the rotating disks. Oh, they provide lots of interesting facilities, query facilities and reporting facilities and all that stuff. And let me rant just for a minute about the absolute insanity of creating a text language to access our data. SQL, a text language to access our data. A language that can be squeezed through the input of our systems and somehow used to pollute and interrogate our systems. SQL injection. Had we thought even for a second about security, we would have realized that we never ever wanted a text-based language to access our data. What do we want to access our data? A software API. Is it fun constructing SQL? Have you ever done that? You know, construct a bunch of SQL. Is that fun? You know, writing the code that constructs all that SQL crap so that some other thing can undo what you just did and understand it, when you could have simply told it. But no, we have to construct. So, I'm sorry, that was a rant. The database is a detail. The database is an I/O device. From your point of view, from the software developer's point of view, the database is there to hold data, not anything else. Oh, you know, querying is fine, but we'll talk about that. If the database is a detail, where do we want it? Well, we want it on the other side of an architectural boundary. We don't want the business rules to know about the database. We certainly don't want the business rule to know about SQL. We don't want the business rule to know about the schema of the database. We just want the database below that architectural boundary. So how do we do that? Well, you see that interface up there called the Entity Gateway? That's an interface that has a method in it for every query that you want to perform. So let's say that you want to get all of the employees who were hired after 1976. You would have a method in there that said, get all employees after, and then you'd pass in a date. Every query that you want to perform is just a method on that entity gateway. Now, I've only drawn one entity gateway. There would actually be many, because you'd probably have lots of different entities, and you'd want to partition them reasonably. But all right, let's say there's this entity gateway, and for every database operation, there is a nice little method on that interface, which of course is not implemented in the interface. And then below the architectural boundary, there's the entity gateway implementation, which implements all those methods to operate on whatever database you currently happen to have. Now, if it's a SQL database, then that's where all the SQL is, down there. It's not above the line. So there's no SQL above that black line. There's also no schema above that black line. I don't want you taking DAOs and passing them across the black line. You know, you've got a relational database and you fetch a bunch of rows out of it and you keep it in a form of rows. I don't want rows crossing that black line. By the time anything crosses that black line, I want them to be objects, not rows. And what are those objects? Well, they're used by the entities. Now, some people would say, well, they are the entities. That's not probably correct, but they are used by the entities. The entities contain business rules, not necessarily business data. Business data will be used by the business rules, so there are probably some little data structures that the entities used that are populated by the database. Yes? Nope, now here, I got to do something. You've asked me a question, and I've been told that I need to throw you a microphone. Are you ready for this? Yeah. Okay. All right, now if I miss him, get ready to catch it and pass it to him. You ready for this? Here we go. I don't know. Yeah, okay, fine. Good.
Okay, thank you. Hi.
You're welcome.
What is your opinion about ORM implementation?
I'm glad you asked me that question. All right, you can just slowly pass that. Well, no, actually just keep it kind of there, and you guys can be responsible for throwing it. Where does the ORM go? What is an ORM? What does ORM stand for? Object Relational Mapper. There's no such thing as an object relational mapper. Right? That doesn't exist. And why doesn't that exist? Because what is an object? An object, from the outside looking in, an object is nothing but a bunch of methods, function calls. An object may contain data, but you're not supposed to know that. And there's no rule that says that an object must contain data. An object can simply use another data structure. So an object is something that contains behavior, not data necessarily. A database contains data, not behavior. So there is no way to map from relational data to object behavior. What an ORM actually does is it fills in data structures. That's all it does. It takes database rows and it fills in data structures, not objects. A lot of people make the mistake that your business objects are the things that the ORM builds. That is probably not the case. What the ORM builds is the business data that gets fed to the business objects, not necessarily by constructor, but through function arguments. Where would the ORM be in this model? Yeah, it's the gateway implementation. It's below the line. The gateway implementation talks to the ORM, which talks to the database. It's below the line. Nothing above the line knows about the ORM. Is anybody using Spring or JSF or any of the, what is it, the JPA, the Java Persistence Engine? Anybody using any of that stuff? All below the line. It all goes below the line. I don't want any vestige of an ORM above the line. The entities don't know about it. The interactors don't know about it. All that stuff stays below the line. Be careful of frameworks. I'll rant about frameworks later. The authors of frameworks do not have your best interest in mind. They have their best interest in mind. And let's see here. Fitness. This is just a little example. Long ago, my son and I started a project called Fitnesse. This was about 2001, so 18 years ago. And Fitnesse was a wiki, and it was also a testing engine. And we decided to build it, and our discussions began around how to store the data. It was a wiki, so we knew we had to store data somewhere. And so we said, well, we've got to have some kind of persistent storage. It's probably going to be a database, and it needs to be open source. And what was the best open source database at the time? It was MySQL. So we said, all right, well, let's get MySQL. We'll get a license to it, and we'll work out the schema. And somebody said in the midst of this discussion, wait a minute, we don't need to do that yet, because there's another problem we can solve first, which is the translation of the wiki markup language into HTML. Now, that's a fairly significant problem. We thought, okay, let's solve that one first, and we'll defer the whole decision for the database until later. So we began, and I can show you the structure. We began by creating a wiki page object, and then we implemented it with a mock. And the mock was just a raw thing that allowed you to put data into the page, but didn't store it or save it or anything like that. Just a single page. It had database functions. You see that save function. It had a bunch more functions too. But it had database functions that just weren't implemented. And for about 3 months, we worked on the problem of translating wiki markup language into HTML. And by the way, we were doing test-driven development. So this was all about writing a test and making a pass, writing a test and making a pass. So we were writing tests and making them pass. And by the time we ran out of tests to write for the wiki markup translation, we said, okay, now we need to get the database because we need persistence. We need to be able to link pages to each other, and that's going to require persistence. And somebody said, well, no, it doesn't require persistence. It just requires multiple pages. And we could put those pages into a hash table and make it pretend like it's a database. And we thought, well, that would be really easy to do. So we created another version of the wiki page called the in-memory page, which used a hash table to allow us to look up all of the wiki pages. And now we kept on writing tests, write tests, make them pass, write tests, make them pass. We could link pages to each other, and we actually got the testing engine running so you could run tests. Took us about a year. But after a year of work, we had the whole system working with all the data being kept in that hash table. Now, that was interesting because we could demonstrate it to people, but it was also deeply frustrating because you couldn't save anything. Turn the computer off and you lost all your data. So in the end, we had finished all of our work on the operation of the system, and now it was time to do the stuff that really did relate to persistence. And we said, all right, it's time to get MySQL out. And Michael Feathers was there at the time. And Michael Feathers said, well, you don't really need to get a database yet because all you need is persistence. And you can get persistence by storing the hash table into a bunch of flat files. And we all kind of crinkled up our noses and said, yeah, but flat files, they're inefficient and they're awful. He said, yeah, but it'll work fine. And then later on, you can get the database in there. And we said, okay, it'd be easy. And he came back a day later with the whole thing running on flat files, and we kept on working. Now we had persistence. Now we could save stuff. We make our tests, make them pass, write tests, make them pass, and we're building more and more of this system. Well, now we can take it on the road. We can demonstrate it to people. It saves the data in the flat files. It's working great. Other people start to use it. They think it's great. A whole big user community begins to grow out. They're all using flat files. It's all terrific. About 3 months later, we looked at it and said, we don't need MySQL at all, do we? We'll just forget about that part. And we did. We just dropped it off the whole project plan for a year. Then it came back. And it came back because one of our users came to us and said, we got to have the pages in a database. Why? CEO says we've got to protect our data assets. I said, well, you can't fight City Hall. Okay, so we told him this structure. We showed him this structure, gave him the source code. It was an open source project anyway. We showed him this structure. He said, all you need to do is make a derivative of wiki page that implements the methods of wiki page to operate MySQL. He came back a couple of days later with the whole thing working in MySQL. We used to ship that as a plugin, but nobody used it, so we dropped it. He dropped it a year later, too. He says it was ridiculous. There's a lesson here. It's a very interesting lesson. When people talk about architecture, they often think that architecture is about making decisions early. It's about making decisions late. A good architecture is a software structure that allows you to defer critical decisions for as long as possible. Defer them to the point where you've got enough information to actually make them or not make them, as the case may be. Architecture allows decisions to be deferred, delayed, until the last responsible moment. This may fly in the face of what you think. You may think, no, you've got to make some of these decisions early. Well, there are some decisions that need to be made early. For example, if you're going to write an application, you probably need to decide what language you're going to write it in pretty early. We made the decision to use Java for Fitnesse. That was a really early decision. But the database decision, which we thought we needed to make early, we were just able to push right off the end of the project. The flat files actually worked better than a database would. It was fascinating to us. There were advantages to using flat files that none of us had ever conceived of before. For example, you can check the whole testing engine into source code control. That one we hadn't even thought of. So there was a lot of very, very powerful benefits to deferring decisions as late as you possibly can. Good architecture maximizes the number of decisions not made. Now, what IDE are you using? IntelliJ, right? Everybody uses IntelliJ? Anybody here using Visual Studio? Ooh, did I talk to you about this before? Did I mention this before? Visual Studio? No. Do you use ReSharper? Yeah. Oh, okay. ReSharper is the plug-in to Visual Studio that's made by the same people who do IntelliJ, and it makes Visual Studio almost usable, right? ReSharper is made by JetBrains. Visual Studio is made by Microsoft. Which of these two organizations has the power to completely screw the other? Microsoft. And why? Because Microsoft, at a moment's notice, can change the interface that ReSharper depends upon. If Microsoft wanted to shut down JetBrains, all they'd have to do is change that interface once a week. Sorry, guys. We changed that interface again. We know you need to implement it, but we changed it anyway. Is there anything JetBrains can do to Microsoft to make Microsoft not release Visual Studio?
JetBrains created their own IDE for .NET now called Rider.
Yes, I know. That was JetBrains' actual defense, right? JetBrains created their own IDE called Rider. And hopefully Microsoft people will use it, but some of them are so hopelessly dependent upon Microsoft, I doubt that'll happen. And I have hopes. Right? Rider's a pretty good tool. But is there anything JetBrains can do immediately without inventing a whole new IDE to stop Visual Studio from being released? And the answer to that is no. So we have a really interesting asymmetry here. Small source code changes to Visual Studio can completely prevent JetBrains from making a release. But there's no source code change JetBrains can make that will prevent Visual Studio from being released. Now, forget about the two organizations. Let's talk about your application. Are there parts of your application that you would like to be robust against the change of something else? Some part of your application can change out here, and this part of the application doesn't care at all. Like Visual Studio doesn't care what happens to JetBrains. Are there parts of your application that you would like to be protected from change out here? And of course there are. Primarily your business rules. You don't want your business rules to be affected by, say the GUI or the database. You'd like to protect your business rules against those kinds of changes. And by the way, graphical user interfaces change for the dumbest of reasons. Did anybody get a change to your iPhone, a while back that just changed the whole way the user interface worked? Changed the shape of the icons, changed the way that your gestures work? Some marketing people go around there, we need to make it new and modern, and so we're going to change the icon shape and move things around. And it's very frustrating if you're a user to have these marketing people think that they're making it better. But anyway, they changed everything in there. Do you hope that the application writers did not have to change all their application code because of the strange change that was made here? And yes, you hope you do. You hope that they had isolated those changes from each other. How do you do that isolation? You make the graphical user interface a plug-in to the business rules. Like JetBrains is a plug-in, ReSharper is a plug-in to Visual Studio. You create a plug-in architecture. How do you create a plug-in architecture? You get all those dependencies pointing in the right direction. If all the dependencies point at the business rules, then everything on the outside of the business rules can plug in. You can build it into a new jar file. Take the whole GUI, put it into a jar file, deploy it independently of the business rules, plug it in. And if you can plug the GUI in, you can unplug it and plug something else in, like a test engine. Test engine could use the same interface that the GUI uses. Or you could plug in a console interface if you wanted a console interface. Or you could plug in a service-oriented interface. If the user interface is a plug-in, you can plug any user interface into it. You'd have to write it, of course, but you can just plug it right in. The business rules don't care. The database can be a plug-in to the business rules. And if the database is a plug-in to the business rules, the database does not have to be a relational database. The database could be flat files. The database could be Mongo or Root or Rinda or any of those crazy NoSQL databases. There's a question over here. Would someone take that thing and throw it over there?
My question is about how do you see the concept of an enterprise bus in relation to the plugin in the architecture?
The enterprise bus. I don't know how much trouble I want to get into. Suffice it to say this: there are problems that occur inside software systems because of fashion. It's a new fashion to have some interesting architecture like a service-oriented architecture. That becomes a fashion statement. And that started about 15 years ago, maybe a little more than that, and everybody had to go service-oriented. And some companies, by the way, there's nothing wrong with being service-oriented. That's an interesting structure. It's an old structure, but it's an interesting structure. Some companies then get the idea that there's a marketing opportunity there, and they make tools that claim to support that architecture. You have to be very careful about that, right? Because these tools are generally not the grand solutions that they claim to be. I'm not going to go much farther than that in my rant against tools for service-oriented architecture and enterprise buses and so on. If you are using an enterprise bus, it's an I/O device. All it's doing is facilitating communications between services. It is an I/O device, and you put it behind a boundary, just like we put the database behind a boundary and the graphical user interface behind a boundary. You don't let any of your business rules know that this bus is there. And then you use the bus for what it's intended as, a communication method between the various services in your system. And by the way, some of those buses are fairly elaborate. They've got nice little tools that allow you to route the messages here and there. And very cool. Okay? Just from the point of view of the code inside the services, they're I/O devices. Keep them below a line. No. Yes, I know, and there's a slide that I wanted to do, but it's not in this presentation, so I'll just do it. Frameworks. Part of the fashion that happens in our industry are various frameworks. And we get very excited about a new framework. Ooh, there's a new framework out there. We ought to try that new framework. It's called Bananas. And we have to come up with these weird names for frameworks, right? So, oh, yeah, let's use the Bananas framework. That's fine. It's okay to be excited about frameworks. But you have to understand that frameworks are not made for your benefit, right? They're made for the author's benefit. And there's a huge asymmetry when it comes to frameworks. In order to use a framework, you must make a huge commitment to them. You're going to be coupling your code into those frameworks at a really detailed level. The instruction manuals for the frameworks encourage active coupling into the framework. They want you to derive from their base classes. They want you to insinuate their code into your code so that the coupling is tight. That benefits the framework authors, does not benefit you. The benefit authors do not necessarily have your best interests in mind because they don't really care if you eventually get your application to a point where the framework is in the way. Now, frameworks have this lovely ability to make the first months of a project easy. But then they make the next years of the project difficult. Because you will want to do things that the framework didn't ever anticipate and is in the way. It gets in your way and it forces you to work around the framework. So you will discover that as you use frameworks more and more and more. And a good architect looks at every framework with a cost-benefit trade-off in mind. How is it going to help me? How is it going to hurt me? And there's always a cost. And a good architect will put a little boundary between the framework and the rest of the production code. That will hamper your use of the framework slightly, but it allows you to decouple from the framework enough so that the framework can stay safe and unintrusive. Remember this always. In order to use a framework, you must commit to them. They do not commit to you. So it's a deep asymmetry and a problem that an architect has to face all the time. Who's using dependency injection? Why? Because it's cool. You're supposed to use dependency injection like, man, it was new a while back, and so we're all using it. But why? It makes a few things easier, doesn't it, right? So what are you using, Spring? And do you use little @AutoWireds? Do you have those little @AutoWireds scattered all through your code? If you look through modules, do you see @AutoWired? Did you see all that stuff scattered through your code? The framework has insinuated itself into your code. Right? Can you imagine trying to get rid of that dependency injection framework? What if there's a better one that comes out? I don't know, we're using this one because the @AutoWired is everywhere. Now, what dependencies should you inject? Everything? Or are there a few key strategic dependencies, a few factories, a few strategies that you could inject into one of the peripheral modules of your system? I like to call that main, by the way. The main module of your system, which is behind a boundary. You could inject a few critical dependencies into that one and then pass those dependencies around the system by normal means, which I know means that you're working in the 1990s and it seems out of date. And on the other hand, it will keep that dependency injection system from infiltrating everywhere. Has anybody had the problem that when you do a build and the build fails, it's because something in the dependency injection scripts and descriptors have gotten screwed up? And you don't know where, it takes a long time to hunt through it, and oh yeah, there's this version and that version and that version, and all that XML gets in the way. Keep that dependency injection small. You don't have to inject everything. You should not inject everything. Inject a few critical things, and then pass everything else around normally. And with that, I think I will conclude. Is there any one more question? There's time for one. Yes?
So what about the...
Take that thing and throw it down to him? Or, oh, there, that's better even.
So about architecture, what about the fourth dimension? So things like concurrency and stuff like that easily lures you into frameworks like reactive because they solve it. But how do you can you fix concurrency in this day and age without frameworks?
Well, I hate to say, so how do you survive in this day and age without frameworks? And the answer to that is, well, you're probably going to have to use some frameworks, but you always want to also be looking at the build-buy decision. The build-buy decision is nowhere near as trivial as you think it is. Right? It is often better to build than to buy, even when you're buying something that's free. Right? So a framework might be free, But the cost of that framework over, say, a 2-year period might be more than the cost of building the solution yourself. Most of the stuff that we use frameworks for is actually pretty simple to build yourself, because the framework author built it himself. It didn't really take that long. Anybody know how many lines of code are in a web server? Minimal web server. Something that'll just serve web pages. It's about 200 lines of code. If all you need to do is serve web pages, you need 200 lines of code. And if it's your code, do you know how far down the security issues go if you wrote that code? You know how far down all the configuration stuff goes if you wrote that code? You know how much easier it gets to manipulate that code if you wrote that code? And how much harder it is for somebody else to break into that code if you wrote that code? There's a lot of advantages to thinking carefully about whether or not you need a framework or whether you could actually build the solution yourself. Sometimes the framework is the right answer. But in our industry, we make the framework decision in the wrong direction way too often. And with that, I will close. Thank you all.